Okay, so hello everyone. We are starting today's lecture. Today we will continue to work with enriched categories. I hope we will finish basic material about them. And I want to start with reminding what we did last time. Last time we had two topics. First topic was monoidal categories, another one was enriched categories. So monoidal categories are categories where we can multiply objects. This multiplication between objects we call tensor product. It has unit, so multiplying with that unit gives us the same object up to isomorphism, and we have associativity, and in symmetric monoidal categories also symmetry of multiplication between objects. This all was stated last time with different notions of uniters, associators, braiding, and so on. That was the beginning. Then we got to so-called coherence, and coherence tells us that any diagram manufactured from identities, from associators, uniters, braidings, their inverses, and so on, actually commutes. That's a great theorem of Maclane that says that every diagram commutes if and only if we have pentagon, hexagon, and a couple other axioms. We don't really need them to go in these axioms. They are good to check whether your category is monoidal or has certain properties, but not conversely. To work with it, we will need every diagram. And then we defined what is an internal home. So internal home is a something that is a function that is adjoined to multiplication or tensoring with certain object, other objects in a category. And yes, usually it's given by home, because tensor is given by tensor in our usual setting of pre-additive, abelian categories, etc. Then we decided to move to enriched categories. So the categories where we can apply things about monoidal categories. So enriched categories are categories where home sets are not sets anymore. They are home objects that are called objects of morphisms. And we needed to redefine what is associativity, what is a composition, what is an identity, what is associativity, unitality, in a category, and we get enriched category. On the right now here, you can see a bunch of examples of categories that are enriched. Enriched where in, no, the setting where in which we can enrich. So we need a base category, monoidal category, and other categories where home objects belong to these categories are getting enriched. And this gives us entrance or exit or bridge to other branches of mathematics. By the way, at any point, if you have any questions, please ask, because some constructions can be a little obscure or not clear. Then we defined what is opposite category. Opposite category is defined where home objects we reverse the order between X and Y in home object in original category, and a little twist composition with using braiding. Tensor product of categories is similar to just Cartesian product of ordinary categories, category of pairs. Home objects are products, are tensor products of home objects. Then we had trivial enriched category. And we stated that our category of small enriched categories is also symmetric monoidal with respect to this operation. Okay, then I defined what is a V functor. V functor is a functor between enriched categories that consists, and now I would again emphasize on the thing that consists of bunch of maps in that are morphisms in your base category V. So before or usually people define action on objects and action on morphisms. Right now, I will breaking action on morphisms as action on every pair of home sets. That's how you should think about that. So action on objects, it's one part of definition. Action on home objects is another part of the definition. Okay, and then I gave you an example of so-called self-enriched category. So closed symmetric monoidal category is getting, it can be promoted to enriched category, enriched in itself, and that's fantastic operation. It's called self-enrichment. So if you are closed symmetric monoidal, you can get rich just thinking about yourself. That's all nice, and today we will continue. I am creating a new board, and today I'm going to start lecture 8. I will make in columns. So lecture 8, it will be about enriched co and calculus. That's a general topic, and this general topic we will break in a couple of pieces of smaller topics. So first subtopic will be about representable V functors. Representable V functors. Okay, earlier, what we had? So part A. If our category Cosmos V is set, we are taking object A belonging to category A, and it gives us A from A to blank is a functor from A to set. This is this functor is called representative. Very nice. How it acts? It takes every object X to set of transformation of morphism from A to X, and every morphism from X to Y, F, will go to a morphism from AX to AY, and this morphism we call F lower star, which is precisely the post-composition with F. So F star of any G, it's FG. Very nice. It's how we define representable function. Now, part B, we need to do this in a little different manner. Where is the problem? The problem is precisely how to define it on morphisms. So we need to move more set of morphisms, not set, object of morphisms from X to Y to something else. Okay, what should we do? We need to think in terms of diagrams. This will help us a little. So when I have morphism from A to X, here belongs morphism G, here will be FG belonging, it's G, then I'm taking F from X to Y, and their composition is FG. Very nice. So the main thing is composition. I am taking set of morphisms from X to Y cross from A to X and going to A from A to Y. To this belongs F, to that belongs G, and there we are getting FG. So here is our composition. sub A, X, Y. I told you that I will be never writing it again, so I did it. I again committed the crime. I named the composition how it should be named. So it's subject to A, X, and Y. Good. If I want to get completely element free, so I won't be ever thinking about elements. Who is bothering me in this construction? Which argument, F or G? Who will tell me? To get element free, whom I need to get rid of, F or G? This is a question to the audience. Everyone can answer or ask. Students, professors. To get element free, whom I need to remove from my picture? Yeah, Sean, you try to answer.
G.
Of course.
Or F.
Of course, you need to move this thing there. So you will just be taking every F, if there is such F, to something, to some function F star. So you need to move that way. Okay, but moving from product to something is using a junction, right? So you are actually doing what? You are going from X to Y. You are moving to the set of functions from where A, from A to X to A, from A to Y, just by a junction. So it will be C, A, X, Y, sharp. Let's call it this way. And this gives F goes to F lower star. Yes, this was quite obvious from the beginning to write this thing, but nobody thinks about this as an adjoint to the composition. But now I put emphasis that it's adjoint to the composition. So right now I can write part C of my not definition, I don't know what, remark, which will give us the representable V functor. A underlined A blank, where it goes and how it acts. So A from A, sorry, total. It goes from a category A to category self-enriched category V. That's why I needed to self-enriched category. Before I was landing in categories of sets, but functors are going between enriched categories. So I can't land in a Cosmos V. I need to promote it to self-enriched category. Good. Object X is going to, let it be not X, let it be right now B, as I want to follow my notes. We'll go to object of morphisms from A to B. And when I take A, B, C, tensor A, B, I have composition C, A, B, C to A, C. This map gives me a joint. It is A, B, C going to internal home V between objects AB, AC. This is C, ABC, sharp. This map is my A comma blank component at BC. So that's how I define enriched home functor, representable enriched home functor. Its component at object of morphism from B to C. Very nice. This I should say that is covariant. Now part D is contravariant, representable V functor. So it will be A blank A from A op to self-enriched V. On objects, it's straightforward how it goes. So B goes to A from B to A. And now on morphisms, we are taking A, C, B, tensor A, A, B. And as you see, it's a little wrong because we need to go from B to A, from A to something. No, we need then use braid in beta. So it will be B to A, tensor A from C to B. Okay, now we have a what map? We have a composition from C and CBA. And to hold this map, I am taking a joint and I'm getting A for CB goes to internal home V between A, BA, A, CA, and here C, AB, beta, sharp, adjoint to it. So this thing all is a component of A blank at BC. I want to remind that this guy is A op from B to C. So this is a contravariant representable function. As you see, every notion is getting a little difficult to write, as you need completely to forget what you are used to in ordinary set. And now I want to give a definition of enriched natural transformation. Once I was given it for the case of usual natural transformations in the form of hexagon, and right now I want to do it again. So alpha from F to G that are acting from A to B is V, a natural transformation. From functor F to functor G acting from enriched category A to enriched category B, if, not if, it consists of, so that's a data, consists of a family of morphisms from identity, from a unit object of monoidal operation to home set B from FA to GA, called beta sub A, such that, and now we will have a hexagon. So A from A to A prime goes to I to A prime. Once we did it, but I need to do it again for the sake of completeness. F of A prime, G A prime, tensor B FA prime, and then it goes to B FA GA prime, and there is other way. Here it will be A prime tensor I, then it goes to other composition B GA prime. I promise you it won't be too much such diagrams only today. I know it's not a fun to write this, but still we need it. Okay, so here is lambda minus 1, here is rho minus 1. So that's a left, that's right unitary inverse. We are creating an identity object, sorry, a unit object. Why? Because we want to pick up, to have a pair. One element of pair, it will be here, beta A prime. Another element in pair, it's a component at A prime of a functor f. Below here, we will have component of a functor g A prime, and then beta sub A. And here will be composition here and composition here. And this diagram commutes. So if you want, we will write this again. So here, this arrow gives. So if you have here morphism f, here it gets to 1 point set f. Here it will go to f 1 point set. Then it will go for us at f of f beta A prime. This arrow, it goes to beta A. Here is g of f. And here they join together in a commutative square. Here is beta A. Here is beta A prime. Here is f of f. Here is g of f. And the square commutes, which is the definition of natural transformation, regular one. That's how we can unpack it. Okay, so this is a natural transformation. Okay, now I will say that there is a certain easier way to write natural transformations between functors that are landing in a self-enriched category V. So if we have alpha from F to G going from A to and self-enriched V, then this family alpha A from unit object I to V from FA GA is in bijection with whom? It is in a bijection with a family of arrows FA to GA that are AA. Let's call them flat. Like flat symbol is in music, this one. How we do this? We are using here a junction. So every morphism from I to, okay, let me write down V, I, V, F, A, G, A is isomorphic to V of I tensor F, A, comma, G, A. And this last is isomorphic to V, F, A, G, A, okay? Is everyone okay with that? So that's how I move alpha sub A to alpha sub A flat. And the diagram star using this thing, star becomes. And now I will write a square which looks significantly simpler. A from A to A prime, V f of A, f of A prime. Here will be V from GA, GA prime, and here will be V f A, G A prime. Here is f A prime, here is G A prime, and here is alpha A prime, alpha A prime lower star, alpha A upper star, as you used to do. Okay, but this should be a little confusing, even if I will say that it's flats. Yes, we have flats. Or do not have flats. No, let's do not write them right now. Why? Because this family of morphisms, this one, it's a family in V, because I and home object belongs to V, so they are in an enriched category. This family also belongs to V, but not just V, V underline. As in V underline, we equip it with a little additional structure. So these are, I would say, this isomorphism that I wrote, it's isomorphism where it's isomorphism in an enriched category. So it's not isomorphism of sets. It is isomorphism of the object. Because this enriched, so our V underline is actually internal home. So for internal home works the same adjunction formula. That I haven't proved that, but it's you can prove it yourself. It's not in set, so it's not in set. That's a huge difference. The thing is not in set. However, still we can do it even in set if one wants. For this, we need, when we cross out this thing here, this here, and this here, it will appear in set. So then I will be able to write this as also family in set. I'm thinking right now aloud with you, okay? But being a family in set from FA to GA, I need to write somehow this upper star and lower star. But whom are they? And here is a very, very big question. So right now the question is the following. How morphism, we are going to another part. So how a morphism from one object to another can induce these maps that we used to in ordinary category theory, like post-multiplication and post-composition and pre-composition. So right now we have a question. How from morphism from F from X to Y induces F lower star, F upper star in an enriched setting? Yes, before we have defined contravariant and covariant representable functions. Still, it gives us no answer how to define separately given one morphism from X to Y, or something that substitutes it, some morphism of what is it, F upper star and F lower star. So this will be our next goal. Once we will do that, we can obtain many easy results and good diagrams. Okay, so construction. Not construction, but construction. Okay. We are given map from a unit object F to A from X1 to X2, and we are given map from identity object I to A, Y1, Y2, G. Goal is to get G lower star and F upper star. Let's do that. So A. We are taking set of morphisms from, not set, object of morphism from X1 to Y1. I'm going to make G star. So G star will need to extend. Okay, let me draw a diagram here. X1 to Y1. There's some that call H. Here goes G to G Y2, and here will be G H, which equals to G star of H. Okay, so that's what I'm trying to do. For this, I'm taking any H, or in other words, objects of morphism from X1 to Y1. Then using lambda minus 1, I'm creating an empty spot next to it. So a unit object I, A from X1 to Y1. Then I can use right now from unit object to create my map G. So from Y1 to Y2, tensor A from X1 to Y1. This is my map G tensor identity. Okay. These all maps are in category V, in monoidal category, in real category. So that's all okay diagram. Then I'm using multiplication, C, and I'm getting to A from X1 to Y2. Then with the red, I will denote a map that is G lower star. So the moral is the following. My map from Y1 to Y2, Y1 to Y2, which is called G, does not exist anymore. Instead of it, I have a pickup or a choice, or call it however you want, from unit object to object of morphism from Y1 to Y2. When you have sets, I is precisely a singleton, so it will be pickup of the map G. And then, having this map, I can induce G lower star, which moves me from one home object to another home object. Well, then right now part B, similar. I can define F upper star. So for F I have here x2 to y2 map. Here will be x1. Here is f. Here is h. Here is a composition hf, which is precisely f upper star of h. So it is a from x2 y2. Here will be rho minus first, inverse of right uniter from x2 to y2 tensor identity unit object. Then here x2 y2 tensor a from x1 to x2. Here will be a x1 y2. Here is again composition, and with the red I am writing f upper star. So here are my induced maps, and I know how to do them. Good. So therefore, the previous diagram, how to write enriched natural transformation in a simpler way, works. Because I know how to define upper and so pre-composition and post-composition given maps from identity from a unit object. I constantly calling it identity. My apologies. From a unit object in a monoidal category to a home object in a given category. The next notion, the next goal is for us, once we decided that we have natural transformations, is to think how natural transformations, functors, and categories work together. About this, I will write a theorem. So I have a theorem that V cat is a two category. It has small V categories, small enriched categories, V functors, and V natural transformations. Together they form two category. Before we said that V cat with respect to, so V cat with respect to tensor product and trivial category I is symmetric monoidal category. So we have a question. Question is the following. Is it closed? Answer: yes. It is closed, symmetric monoidal category. So we have a closed structure for V category. And I would say that morphism set. So it's a functor category. Functor category is a V category whose home objects are from F to G. If you are thinking about V natural transformations, I would disappoint you. No. You should think about something else. It is given by N over A B F A G A. Before, this was a theorem that for in case of sets and of the following bifunctor, B twisted with fg, it gives us a set of natural transformations from functor f to functor g. Right now, this gives us a definition, but this is a definition of what? Of home object in a V category of functors from A to B. So our functor category is being promoted to V category. Before, we could state that it's has something, but not V category, because V category has home objects as objects of Cosmos. To get home objects being objects of Cosmos, we use AND. And this is enriched AND. So what is enriched AND is the next our goal. So I would say it right now, it's part 2, enriched ANDs. Okay. So to define enriched ANDs, we need to define something that substitutes wedges. So before we had what? We had TA prime A prime, TA A, here will be TA A prime, yes? And here was AND over A, TA. Here we had eta sub A prime, here eta sub A, and there were two maps induced by map F. So here was T F A prime, here was T A F, and where F was going from A to A prime. And this object was universal with respect to making such diagrams commutative. So AND was going before we had, so that TA op cross A to B was given by AND TAA together with a family from maps from our AND TAA to TAA values, diagonal values, TAA, which are indexed by objects A. So this was AND. And that object was terminal wedge. What was wedge? Wedge was given by, defined by dinatural transformations from delta sub D to our functor T. Subnode D, let's B. We have category B, so B. And this was dinatural. We have issue. There are no constant functors in enriched categories. Why? Here, look what we did. Before we had category A going to trivial category, going to category B. So this was before. This picks up object B. This is a trivial unique functor. And this functor was called delta sub B. This was before. Now we have A. Here we have B. We have B, and let me move a little screen. And now below we have trivial category I. Okay, from trivial category I to B, functor to B is precisely will be B. But here, if it was before exclamation mark shrink, that meant unique one. Here right now we have a question mark. Why? Because functors from category A to trivial category I are given by A from X to Y to I question mark of X question mark of Y. But this is a trivial category where this is just a unique object star. It's unique object star, and the unique object star has trivial object of morphisms from it to itself. It's I. So this is the question mark sub X sub Y. So we need some family of maps satisfying functor properties from a home object to I. And this, I will write here 3 question marks circled. We don't know it. We have no idea what is it. We can define a functor to a trivial category. Isn't it hilarious? If our I was terminal object, then it would be fine, because to terminal object we always have a unique arrow. That's okay. Unless I is a trivial object, we have no right to talk about constant functors. So here I will use another color and say that there are no constant functor, because we do not have in general a functor from any category to a trivial category. It's not an open question. That's a question of structure. We don't necessarily have it. If I is terminal, yes, we would have something, but still it will be only a substitution. The best case scenario is to have so-called Cartesian structure on closed symmetric monoidal category V. So Cartesian structure means that product plays role of tensor product, and terminal object and unit of this operation is a terminal object. But this is not really always the case. It's a case for sets, and I will have hard time to think about other cases. For instance, in Z, this is completely not correct. So imagine that here this, instead of this object I is Z. So you have a Abelian group of morphisms from X to Y, and you need to take some family of morphisms to Z. Do you have any idea what to do with that? I don't think so. Neither me. So there are no constant functors. Therefore, we need to define wedges, and not only wedges, all theory of ends, coends, limits, colimits in a very different way. So what we need? Define wedges in a different way. How will we do that? We'll define the following notion, which will be called V natural family of maps. So Let T from A of tensor A to B, all enriched categories, be V function. Let B belongs to category B, an object. A family of maps from B, A sub alpha to diagonal morphism TAA sub A in V is said to be V natural in A if the following diagram commutes. If the following diagram commutes. We are taking A from A to A prime, making arrow to B, here T, A prime. I will explain what is going on in a couple of minutes. TA, A prime. Here is B, T, A prime, T, A prime. And here is B, from B to TA, A prime. Is it correct? Right, that's correct. And maps. So our functor, bifunctor T, can have, we can fix in it one of the arguments. So we are fixing first argument A, or here we will fix the lower argument A and take component at A prime. How we obtain partial functors in this completely similar manner to our representable functors. That's how we obtain TA, upper blank, lower blank. And here we will have alpha sub A upper star, and here we will have alpha sub A prime, also upper star. Okay, so let's look closely what's happened. So we have a map from A to A prime. Let's call this map F. Going in upper vertical arrow, we will get T A to T A prime. It will be here T A F. Going down, we obtain this T F, here A prime. As you see, these are the maps that appear in the notion of wedge. So these are legs, not legs. This is a base for wedge when we define wedge. And then these maps are going to be multiplied, being precomposed with alpha alpha A or alpha A prime. So here, in this case, we will get here T A F, T F A prime. Here is my alpha A prime, here is alpha A. And this diagram should commute. That's what we had in our usual definition of wedge. So no denatural transformation, nothing. Just this definition. Here is object B. I want to emphasize on this. Here is object B. This diagram, what I draw here, where it commutes in V. So this is a commutative diagram in a symmetric monoidal category, not enriched, but just category. There it commutes. And here is a notion of V natural family of maps. So it's precisely a family of maps that before constituted a wedge for us. I will cross it out, that we won't think about this as a part of definition. So before, this was a legs of wedge. Before. Okay, the next step is to define the end, but for only certain type of functors. So next step is definition. And we have let T A op tensor A to self-enriched V be a V functor. And of T is defined now as, of course, object defined using integral TAA with family of maps. I will a little abuse, so I won't be writing object separately. Two diagonal values, TAA. These maps, yeah, let's call them eta sub A, is a V natural family of maps such that for any V natural family, let's call it V psi I to T AA sub A, it's V natural. There exists unique H such that the following diagram commutes. Here is V, here is our end, here is our TAA, here is our eta sub A, here are my psi A, and here is unique H. And this diagram commutes in category V, because these are maps in ordinary category, in category V. So therefore, I decided that and equals first part A, V natural family, and B, which is terminal. So my step forward from the original definition was was in the fact that I I redefined legs of wedge separately as V natural family. I can do this when my functor excuse me, maybe I did a mistake. 1 second. Let's think about the following. In the definition of V natural family, I decided to take functor from A op cross A to B. Could I do that? Yes, I could do that. That's okay. So the main that the diagram, my diagram here that I'm right now drawing, belongs to category V. That's fine because objects, home objects in B are again in V. That's okay. That's all completely fine. Good. So I substituted legs with V natural family, legs of and the property that is terminal is kept because we are deciding this in ordinary category V. So I will again write down this. It's ordinary. Okay. Well, then you can ask me why we are we so much bounded that we can define ends only of functors landing in a self-enriched category V? No. Right now, we will define it for any functor using the previous definitions. Again, so let T from A op cross A to B be a V functor. Then, not then, not the end of T is given by a V natural family TAA to TAA eta sub A such that for every object B belonging to category B, and now you can feel a huge satisfaction. What will happen? The following family, B from B to end, to a candidate to end, TAA, and this is B. Here is alpha, sorry, not alpha, eta A lower star, right? Sub A is end of functor B, T blank double blank from A op cross A to V. That's hilarious. We have defined end of a functor landing in a self-enriched category. And to define end of any functor, we compose it. It's nothing else that just compose it with representable function and check whether the natural family that we picked up will induce end of that composition. So the end of functor is being checked using representables, or representables define who will be end or not. Before we had no idea, no chance to do that. But in enriched category series, it's the only way how we can do this. That's how we proceed. And this is end. It would be very sad if our end defined this way won't have the same properties as we used to in usual end coend calculus. I not only promise, I'll tell you that it has all the properties that you expect. All the same properties. Just all categories are getting enriched, and all functors are getting to be enriched. Lemma, small lemma, that in general, end of a functor this end is given by equalizer in a category V. Here is product over A, B, FA, GA, 2, the product V, here A prime, to B, F of A, GA prime. The maps are the same as before. So upper and lower star. Here, of course, it's over A prime. The same as we did when we decided to write end as equalizer with products using equalizers and products. And of course, theorem V cat tensor trivial category and brackets is a closed symmetric monoidal category where this is given by end FA GA, and you are free to compute it either using equalizer or general definition using V natural families. Of course, we have properties. These properties are straightforward. I will write them, immediately down. That home internal home from trivial category to category A is isomorphic to A, and we have that A tensor B C A B C. That's what you can expect from internal home, and indeed you have it. Are there any questions? Well, if there are no questions, then I will make, I guess, can I move the screen up? Okay, if there are objections, please tell me. I want to make move a screen up and tell you that coends are defined similarly. There we will use V natural family of morphisms ending in a fixed object. Then which will have initial property. And for general coends of functors landing in a general category B, we will also use representative. Nothing else. But there, by representables, we also will use covariant covariant functors, yes, and whether it will be end or no, we will use contravariant. I guess we will use contravariant functor and check whether the result will be end. But never mind, you can always think about your coends similar in a similar manner. Now, what we have enriched Unada lemma. So next part is enriched co-Unada lemma. I'm thinking, will I be able to write now enriched co-Unada? 1 second. Yes, since I said that we have coends defined similarly, I can do it. So lemma Unada. What we have? So let f from A to base category V, and A belong to A. So this is a V functor. This is object of enriched category. Then we have an isomorphism. F of A is isomorphic to A set of natural transformations from covariant enriched representable functor to functor F, which is, I want to remind you, given by end in this way. And this isomorphism is natural, is not natural, is V natural in A and F. Okay, so every isomorphism is a map So we have a family of maps indexed by object A, and we can talk about V naturality in A of this family. The same as this map is indexed by F, and we can talk about V naturality in F. The same way we defined V naturality. That's all very nice. Of course, we have corollary. What is the corollary? That A to A prime is isomorphic to AV, A prime blank, A blank. The same as we had before. This was UNEDA covariant. Now let's write lemma UNEDA contravariant. It will be if G is from A up to V, A belongs to A, then we have G of A is isomorphic to natural transformations A up to V from A blank A, G, which is given by end sub X, V A X A GX. This is contravariant UNEDA lemma. Right now, you will ask me, wow, what is co-UNEDA lemma? And co-UNEDA lemma will be given by coend. 1 second, I will open its statement. Don't want to confuse anyone. Okay. So next thing is lemma. We'll call it co-UNEDA covariant. It tells us that if we have F from A to V and object A belongs to A, then we have the following isomorphism, that F of A is isomorphic to coend. Here let's put X, Fx tensor A X to A. And again, it's V natural in A and F. So what do you see right now? You see that we have changed end by coend, and under the end was internal home. Now it appears it is tensor product. This functor F blank tensor A double blank A is actually a functor from A. No, let me write here double blank, here single blank. A op cross A to V. So this is indeed a bifunctor where first argument is with op, another with without op. This is very important. Otherwise, we won't be able to take AND or coAND. Moreover, I will tell you that here functor f is covariant. So this is covariant. And that one functor is contravariant. In previous lemma, Uneda lemma, we had that both these functors were covariant. But because of being on a first contravariant argument, covariant functor became contravariant. I mean, the dependence on x became contravariant. Okay, and now another lemma, which is called Coyoneda, contravariant. It tells us if G is going from A op to V and A belongs to A, then G of A is isomorphic to coAND over X. Here will be G sub X tensor A X A. And again, this is a functor, well-defined functor from A op cross A to well, okay, very nice. And what I would say that from this moment we can use all coAND calculus formulas as we had before. So we will finish this lecture. We have still 5 minutes. So we will have coAND calculus. First is co-Uneda lemmas. Second is that natural transformations from A to B, from F to G, is given by AND, B, FA, GA. Third, that if we have T from A op cross A to B, then for every B belonging to category B, B and sub A, T, AA is isomorphic to AND over A, B, B, T, AA. That's a definition, how we have defined our AND of functor with which lands in arbitrary enriched category, and also B here coAND TAA comma B is defined to be an AND over A. Here will be B TAA comma B. So ANDs are going as itself, and coANDs are turning into ANDs when they are at the contravariant argument. There are more rules. Are coming from can extensions. Weighted colimits and profunctors. But the main here is weighted limits and colimits. Thank you for attention. That's all for today. Next time I will think what will be either can extensions or profunctors, or weighted limits, colimits plus can extensions. I will think a little bit. As I understand, we still have 3 or 4 lectures left. I hope this number is 4, not 3. So I would be happy if we have 4 lectures. I will get to my final point. We have also topic that's called tensor home cotensor, which just joins everything together, what we know up to now. And I'm not sure how I will get to it and in which way. So next time will be either can extensions or profunctors, I think this way. And after this, then after both these topics will be weighted limits, colimits, and tensor home cotensor. Maybe I will shrink a little, not a little, significantly can extensions and talk more about profunctors, as I found them more important up to now. Can extensions are great, but it's so infinite topic that we can have a full course just about can extension. So thank you again very much. If you have any questions, you are welcome to ask. Any questions? If you are wondering how to compute coends, I will answer you on when we will study profunctors. If you are wondering how to compute ends, try every time think and somehow to tie it together to natural transformations. If you are wondering that ends are end is over A, it's a universal functor, and coend over A, it's an existence quantifier. Sorry, these are relations. So you always can think about that. Okay, if there are no questions, that I'm stopping my